Right, welcome back. So now let's take a look at how do we actually implement security? How do we implement logins and things like that on the server side? So let's start with one of the most important aspects of implementing security, and that is passwords. What are we going to do? Right, HTTPS was about how do we get the password safely from the browser to the server. But now that we've done that, the server's got the password, right? It's traveled via post, protected and encrypted via HTTPS. The server now has it. But what is it going to do with it? Well, typically we need to store that password somewhere in a database, right? Maybe there's a registration process or something like that. So the password needs to be stored. But how do we do this? Well, as it says right here, the key thing here is that passwords must never, ever, ever be stored in plain text. Because if anyone gains access to that database, then they'll have access to everyone's password. Okay? So the alternative is to, instead of storing the plain text password, is what we store in our database is something called a digest. And a digest is the output of a one-way hash function. So here we've got our original password. So that's the password that we've received from the browser. Okay, we run it through a hashing function, and it outputs some kind of digest. That digest is what we're going to is what we're going to store in our database. Most common hash functions turn an arbitrary amount of text into a fixed size digest, say 32 or 64 characters. They're kind of magical in many ways. The MD5 hashing function was kind of the standard hashing function to use for many, many years. You may have heard me say at one point that HTTPS uses the SHA-256 to hash the public key in the certificates. There's also a SHA-512, a SHA-1. I think there's, I don't know, SHA-32. There's a variety of other variants of that particular hashing function. And more recently, there's been a series of ones known as, often known as bcrypt in some form or another. Well, it says right up here, not all hashing functions can be trusted. And unfortunately, hashing functions are vulnerable to two different types of attacks. There's rainbow table attacks and old-fashioned brute force attacks. So let's take a look at rainbow table attacks first. What's a rainbow table? It sounds so pleasant, but a rainbow table is just a special type of table in which the plain text version of a hash can be looked up. So in our example here, right, let's say 1, 2, 3, 4, 5, 6, 7, 8 characters. Let's imagine that this rainbow table has a list of 8, so 1 to 8 characters. And so it just kind of goes through each possible permutation and combination, specifying, let's say, the MD5 digest. So these files are thus quite large, right? Often hundreds of gigabytes in size, and it can be time-consuming to search through them, but they do provide, as it says, a really commonly available technique for decrypting MD5 hashed values. You may have encountered or looked at some of these or made use of a rainbow table without you knowing it if you ever used an online decryptor for, say, an MD5 hash. So in this particular case, I've pasted in this particular hash. It tells me that it's looked at, what, 17 billion hashes, and boom, it found the decrypted version of it, and that literally took only a few seconds. So in order to protect against rainbow tables, it's common to make a password more complex, more than eight characters. by concatenating on something called a salt to the password before hashing. So a salt's typically 32 or 64 characters of random text. So then the salt and the original password are concatenated together. That concatenated string is then fed through the hash function, and then both the digest that's right that came out of the hash function and the salt must be stored in the database. So let's take a look. Right, here's the original password that the user typed in that we received from HTTPS post. Here's a random salt that's been generated. We're going to concatenate those two together and put them through a hashing function. Of course, this hashing function produces a digest, so that digest gets saved in the database, but also the salt that was used gets saved in the database. The value of this is that it makes it much less likely that this digest is going to show up in a rainbow table. And indeed, I tried putting that same digest into one of these decrypting websites, and none of them were able to find it, right? They weren't able to find it, even in those 17 billion decrypted hashes. So by making a password long and complex, right, instead of forcing the user to type in a 40-character password, salting protects, we artificially make the password complex. And this tends to protect leaked passwords against rainbow table decryption. Remember, the whole point of this is what happens if our password data gets leaked somehow? How can we protect it? So what would that PHP look like? Well, let's take a look, right? It's so here so basically we're gonna need to do two different queries. The first query is that we're just going to retrieve the salt for a specified username or email. Okay, so then we execute, we retrieve just that one column, just the salt. We then concatenate that retrieved salt for this user to whatever password the user entered. We then put that complex password in through our hashing function. That gives us our digest. And then we can do another query. Oops. Then we can do another query where, again, we take the username or email or whatever we're using and this digest to see if they both exist. And if they do, then we know that this is a valid user and we can log them on. Okay, so this is for logging a user in. So you remember there was two vulnerabilities to hashing functions. The first was a rainbow table attack. And the second is a brute force attack. So the other vulnerability of a hash digest are brute force attacks. And instead of looking up a digest in a rainbow table, one can instead just write a simple loop that runs hashing functions on each possible permutation and combination of a password. So here's a kind of pseudocode where we're just going to loop through, we're just going to get the next possible password, maybe by changing a letter at a time, trying this new one through our hashing function, and then checking, is that the right, do we have a match in the digest? And if we do, we found it. So in a sense, that's all a brute force attack is. This is to protect, once again, against a leaked set of passwords, right? A leaked password table where we've got a whole swack of digests and we're trying to protect those digests against the person who's managed to get access to our database. So the problem with a brute force attack is that potentially using assault doesn't help. Why not? Well, the problem is that some hashing functions, for instance MD5, is like its main virtue is that it's fast. And that fast, its speed there is an actual vulnerability. So with modern computers, modern GPUs, parallel processing, and so on, a digest, even with a complex salt, could potentially be cracked in a few months. You might think, well, a few months. And that is generally pretty good. But you do have to remember that the power of CPUs and GPUs keeps getting better, right? The Moore's law about every 18 months or so, doubling of speed. Well, that means maybe within 3 to 4 years, the time to crack with even with a complex salt might be down to a few days instead. Okay, that's a lot more worrisome. So the solution in that particular case is to actually use a slow hashing function. I really love this because it's one of these rare situations in computing where slow is best. And in this particular case, the bcrypt hashing function is ideal because you have the ability to customize how slow it is. The bcrypt hashing function also adds in its own salt. It has a parameter known as a cost factor, which is a number between 1 and 20, so you can sort of decide. So, for instance, if you use the number 10, it takes kind of on average about 50 milliseconds to calculate the digest. That's pretty fast. 12, okay, well, 250 milliseconds. We have to compare that to bcrypt, which might be maybe 5 milliseconds to calculate a hash. So this suddenly changes a brute force solution from taking a few months to maybe taking over a year. That's probably good enough. But again, maybe in 4 or 5 years, the CPUs will be sufficiently powerful that we might want to use even slower. So maybe taking a full second to calculate the hash, that's probably going to protect us well into the next decade, maybe even for sure. Now, let's think about the time. What this means is when we're doing the user registration and the user login, if we used 14, there's going to be a 1 second delay while it calculates the digest. Well, users generally are accustomed to having a delay at a user registration or at a user login. Those are kind of things that you do just once. So a 1 second delay or a quarter second delay or a half second delay isn't that big of a deal. So bcrypt is definitely the way to go. So let's take a look at the code. So the very first thing that we have to do, this is our same validate user. We can make use of this password underscore hash function in PHP, which makes use of bcrypt. We pass in the password. We can specify that, yeah, indeed, bcrypt is what we want to use. And then we can specify a cost factor. And again, this number can be anything between 1 and 20. We only need to do one query, which is an improvement over the previous version with salts, where we had to do 2. And again, we just sort of are going to retrieve the a username and password, and we're just going to see if that password matches the calculated bcrypt digest. So it's actually a nice simple bit of code. All right, that's that.